Welcome to an important lecture on multiple regression and predictive analytics. And then in the next lecture, we'll look at logistic regression and its application in predictive analytics as well. So many problems of modern day machine learning require multiple regression. So by that, I just mean more than one independent explanatory variable or more than one factor that affects your response or outcome variable. So in finance, things like multi-factor asset pricing models is one big class of models. Lots of logistics and economics and demand prediction models to hopefully formulate pricing strategies. We'll look at an orange juice data set in this lecture. And then there's a huge number of internet analytics type problems, Google, Facebook, those types of problems. So what do I like? Type questions, suggestions rather than search. That's all over the internet. Recommender systems, we've talked a bit about that. Netflix, Zillow, companies like that. Alexa. How smart are these AI algorithms becoming? Are they smart enough to be able to book me a Christmas vacation or buy my best friend a birthday present without me having to come up with the ideas? Okay. What are the R commands? Well, we've seen the top one. We've seen the linear model command. One we'll see in the next couple of weeks is the generalized linear model command for logistic regression. And one that we'll see today will be what happens when we have p variables. Now, again, don't forget our plot model diagnostics. Don't forget our Cook's distance. Don't forget our outliers. All of our coefficients will be found in the summary command. And don't forget that we can do prediction as well. Exactly the same as we did before in simple linear regression, and also exactly the same as before with transform variables. So the basic idea of machine learning is I have some output or response variable y, and I have a bunch of input variables, and I have some empirical data set. So I have yi, remember x is a big vector, I have yi, xi pairs, I have a bunch of, I have a training data set. I have a bunch of test cases, and from that I want to build a theory by essentially pattern matching, by empirical pattern matching. Now, of course, the general form would be something like y is equal to some function of those input variables, and I'd love to know that function. The most general form of model would be a deep learning model. In this lecture here, we'll just look at the multiple regression model, where we have a conditionally linear model. And the interesting thing here is that given our empirical data set, given our test data set, we'll be able to estimate all of our parameters. And remember that, for example, beta 2 is estimating the marginal effect of variable x2, holding the other variables constant. So as x2 moves up 1 unit, holding everything else constant, we'd expect the response to move up beta 2 units. Okay, so there's our what's known as our MLR, our multiple regression model. We'll add the typical error term. Again, we'll assume that our errors are normally distributed with mean 0, variance sigma squared. Again, we'll estimate sigma squared by s squared. And with a normal error term, again, we'll optimally estimate our parameters using least squares. So Gauss's least squares equally applies to multiple regression as it does to linear regression. Just one aside, there's a lot of statistical significance techniques that we've learned. Remember, in multiple regression, I like to use the condition that if the absolute value of the t-ratio is less than 1.5, then essentially I'm going to set my betas to be 0. That's going to be my variable selection criterion. But there's many others that people have studied. I think, as I said before, 1.96 is maybe a little bit too extreme. It's hard to measure these marginal effects unless you have very large amounts of data. And as a general rule, I don't really want to throw out variables if I don't have to. Remember, they're marginal effects of variables. And if I ran, it would be a mistake to run the variables individually. It's really the marginal effect. So the individual effects can have different signs from the marginal effects, because as you've incorporated more variables, you're essentially finding the effect of that variable holding the other variable constant. So be careful with that. I like to start with the kitchen sink regression by putting all the variables in at once. So I don't like to do these forward selection type techniques. And then again, another rather important point is, the name of the game really is prediction and economic significance. So the magnitudes of the beta hats and the predictions. So keep that in the back of your mind as well. Don't be totally locked into your statistical significance criteria. And then at the end of the day, as with all of these things, with the diagnostics, with the interpreting models, with the variable selection, at the end of the day, use your judgment, and prediction will be a good equalizer of models. Okay, as I think I've said down here, so model prediction is the great equalizer, and that's one big thing that the machine learning literature has brought to the statistics literature, that looking at out of sample predictive mean squared error is typically a good way of helping you train models via cross validation, and a good way of not overfitting data. And it's good to understand the goal, that the goal really is to find models with good predictive abilities. I remember that there's a reason we do multiple regression, not all the simple regressions. It takes into account the correlation between all the factors, so it shouldn't worry you that the factors are correlated. Now, in some instances, there's something called multicollinearity, when the correlation between the factors is extremely high, and there's something called variance inflation factors and other methods to deal with that. But as a general rule, don't worry that should be correlation between variables, and multiple regression is the tool for parsing that out. And again, as I've already said, running all the simple regressions will give you the wrong beta hat, so don't do that. And as I said, this marginal effect idea, one variable might be insignificant once you've incorporated more important predictor variables. Okay, so let me start with a marketing example. There was a 6-month market test of a new food product. It was a new breakfast cereal, and the idea was to build a multiple regression to give us good sales forecasts. Now, I think we talked back in chapter 3 about observational versus field studies, so design of experiments. So what's nice here is that this is a controlled experiment where you can decide how to collect the data before you start. So chosen by the analysis, so providing good data. But remember, more costly as a general rule to do design of experiments than just to take some observational data. So here's the name of the game. I want to predict sales of a new breakfast cereal. The second you see a sales and price variables, you're typically thinking in terms of logs. I want to work out elasticities of variables. So I've got price, advertising, location in the store, neighborhood income, and size of the store. And just quickly looking down, I've got two what's known as dummy variables. We'll talk about those in a minute. A dummy variable is just a variable that's switched on or off, a 0 or a 1, essentially giving you two different groups. So you would not take logs of dummy variables, but all the other variables you would look at, you would think of taking logs. Remember, that's logs to the base E. Okay, so the whole goal is, can I predict sales? So here's a bunch of questions that you might want to look at. What happens if I don't incorporate all the variables? You're not going to get the right answer, so we'll take a quick look at that. Then we're going to put everything in, run the kitchen sink, perform diagnostics. Then we're going to, if our diagnostics don't check out, we'll look to see what transformations we should use, rerun the new model, perform variable selection, find any influential points, maybe look at outliers, then provide a summary of coefficients and significance, and then the name of the game, why are we building a model to predict sales, is that you can then do company-wide, store-wide predictions for each store, given a price level, advertising level, income level, and dollar volume. or size of the store, you can predict what sales would be. And again, you can understand the policy implications of, do you pay for the high level of advertising or not? So you can also assess the value of that. Okay, well, let's start off with a correlation matrix, sort of an interesting one. There's a whole bunch of zeros here, and that's basically by design. Remember, advertising and location as 0, 1 variables. The company looked at, I think, 72 stores and was able to equally proportion across all possible combinations. So by definition, we started off with a 0 correlation, and then it'll take account of these other correlations down here. Now, one rather interesting feature is that there was a large negative correlation between the level of advertising and size and income of the stores. Maybe if the study was designed again, people might want to try and balance the design over that too, because you'd rather the high level of advertising going to the higher income and bigger stores, just to see what the effect would be. So, but regression will still take account of it. So as I said before, there's no correlation in the X's by design. What happens if I run the regression? Well, it's not going to pick up the effects. We haven't incorporated all of the X variables, so you're not getting the right answer. The economist is happy because his price has got his large negative coefficient. If you increase price, on average sales will decrease, and the marketing person unhappy because I haven't incorporated all of my X variables. So what happens when I go to a more sensible model? And again, I'm predicting demand. It's a sales regression. So I might want to look on a log scale, log sales on log price, on log income, and log dollar volume. And now I get more meaningful T ratios. Why not logs of advertising and location? Because they're dummies, they're dummy variables, 0 or 1. So I can't take log of a 0. Rather interestingly, the coefficient of log dollar volume is 1. And so, as you double the size of the store, you would double the sales. So that would make sense. Really, I should look at my diagnostics first, so to see what's happened. These diagnostics look just fine. If I go to the regression equation that I obtain, I have an equation that looks something like this. The location variable, let us just check, doesn't really matter. It was a new breakfast cereal that was either in the bread section or the breakfast section. Doesn't really matter where you put it, so that in theory should be deleted. One other little minor aside. I want to control for log income for the income across neighborhoods. So even though that's not statistically significant, it's still an economically important variable to put in. So I'm not going to delete that just because it has a negative T ratio. Remember to use a little bit of common sense, and remember my magic level of 1.5, the advertising variable, is essentially bang smack on that. The economic significance we'll see in a minute on a log scale is 0.149. So on a non-log scale, it would be e to the 0.149, which is about a 15% increase in sales. So quite a significant, economically significant level. So again, something that I will keep in the regression. And so remember that there's this duality between if I run a regression on a log scale to if I transform back, anything that was a log-log will end up as a power. So we see that we have 3 power relationships. Anything that was a log and an untransformed will end up as an exponential. And again, in the power case, these coefficients here are elasticities. So let's see what a 10% increase in price would lead to a 17.4% drop in sales. So that's how to interpret the model. Again, we have a couple of takeaways from the model. So a 1% increase in price, I think I just said that, would drop sales minus 1.74. And if I flip advertising to the expensive level, then I'll have an increase of sales of about 16%, and the location is statistically insignificant. So lots of supermarkets, people pay for shelf space or pay for location and positioning in the store, so no need to do that. Okay, so there's a good example of multiple regression. Just to quickly recap, the difference between multiple and simple regression is essentially that you get a whole table of coefficients and betas for each of the variables. So here's all my estimates in this column. Each estimate has a standard error. How accurately have I measured that? If I take the ratio, I get the t ratio, and my rule of significance is anything with a t ratio bigger than 1.5, I'm keeping in my model, and hand in hand with the t ratio, I get a corresponding p-value. Low p ratios mean that variables are significant. So, for example, the size of the store has a very high t ratio of 4, and correspondingly a very low p ratio. Okay, one final thing. A model is only as good as its predictions. So let's use the predict.lm command. So I have to input new data. So I want a price level of 30, advertising switch to the high level, an income of 8 and a dollar volume, a size of the store of 34. I put that into my predict.lm and I get my fitted value. Remember that that's on a log scale. So down here, what's my best guess at sales? It's e to the 5.25. It's basically 192.4. And together with my fitted value, every number in stats has its own standard error to go with it to say how accurately, with that model and data set you've measured it, I've got a pretty accurate estimate of the fitted value on the fitted line, partly because I'm predicting pretty much in the center of my data. So standard error of the fit is only 0.05. And my prediction interval, remember the formula for the prediction interval, it incorporates an extra level of S, the standard deviation left about the regression line, and so little s gauges how tight you will measure your prediction bounds, and it's moderately wide. So even though standard error fit is small, I estimate pretty well on average what would happen. But if I wanted to predict for a particular store, I'd have a band that would go from like 4.7 to 5.7. Okay, so let me now move on and talk about two other topics, something called interaction terms and something called dummy variables. And they're very useful, and they're in lots of regressions nowadays, particularly internet regressions. Maybe I've got dummy variables for day of the week, or dummy variables for brand of a good, or store level dummies. And it can answer lots of questions. So, for example, does gender change the effect of education on wages, or do patients recover faster when taking drug A? Or how does advertising, we just saw that in new food, affect price sensitivity? So we would build essentially a kitchen sink model with all possible dummy variables that get put in. And what would regressions look like that have interactions in them? So suppose I have two variables, and they could be dummy variables, but suppose they interact when predicting y. And all that really means is I have a third term, beta 3 times the product of the two, times x1 times x2. And again, in R notation, if I use the star command, I will essentially be getting all three terms as above. If I use the semicolon command, I'm only getting the interaction term. And beta 3 is significant if there is an interaction term. And as a general rule, statisticians will leave beta 1 and beta 2 in the model if I have a significant interaction term, beta 3. Okay, what happens if one of those interaction terms is a dummy variable? So I'll use D for a dummy variable, and by that I mean that the dummy variable either takes values 0 or 1. So, economic expansion or economic contraction, or world war, not world war, or et cetera, et cetera. And you'll see in a minute how do we do dummies when you've got multiple possible categories. So if I add this term in here, I essentially have an interaction term with x1 times dummy. So let's look at the two cases. So when dummy is equal to 0, let's just plug into the equation. I get y is equal to beta 0 plus beta 1 x. Dummy is 0, so that term disappears, plus error. So that's the case when dummy is equal to 0. What happens when dummy is 1? I get beta 0 plus beta 1 x1 plus beta 2 x1 plus error. So I get y is equal to beta 0 plus the sum of the two times x1 plus error. And that's when dummy is equal to 1. So essentially the effect of incorporating a dummy here is just to change the slope of the line when I switch on the dummy variable. So beta 2 will tell me the difference in slopes of the line. So it's a very useful technique to add in interactions of x variables with dummies. So let me give an example of that. Predicting demand for orange juice across Dominic's stores in Chicago. So let's take a little look. Let's look at the data. I've got 3 different brands, Minute Maid, Tropicana, and Dominic's own brand. So I think there's green, red, and yellow. And you see that my data is quite skewed. So you're going to see that taking logs will be valuable. So let me take logs. So the move variable is essentially measuring sales. So I've taken logs and it's crushed the scale of the x-axis. So here I've gone to a set of curves that looks like this. Still not a straight line. I've just done log sales on price. So I've cut the sales variable down. The sales up here was extremely high. After taking logs, it's a lot lower. And you're going to see in a second I'm going to take log of price as well. So I haven't quite made them linear, but they look much better. If I thought about plotting a curve through that, it would still be curved. So let me do logs on logs. And again, I'm going to go a little bit further than just putting one curve. I'm going to use dummy variables, and I'm going to have essentially 3 straight lines I want to fit to my orange juice data. So I'm going to use essentially a power model, multiplicative rather than additive. That will let me assess what the price elasticity is, and essentially I'm running log sales on log price. And I'll add the dummy so I can essentially get 3 regression lines. We can also look at the effects of advertising, so a feature or not a feature. So we can add that in as another dummy variable. So I can run sales, and essentially the feature variable flipping on and off is essentially changing that underlying coefficient, that underlying intercept of how much I sell. And then I can also do the same thing too, that maybe adding the feature changes the price elasticity of the goods. So I can also add in feature times log price as a beta 4 variable. So I can essentially get a regression model where my coefficient is able to switch. So that's another nice clever insight. Again, if I run the regression for this particular data set, I find that advertising increases price sensitivity from minus 0.96 to minus 1.94. So that's sort of interesting. If I plot box plots, why was price lower during advertising campaign? If I look to see across the 3 brands, I'm going to figure it out per brand. 0 is not featured, and 1 is featured. So I'm dropping price to see if I can sell more. And let's go across the 3 brands. Now I can't just add brand as a variable. Brand's not really a number, so I have to code. Now I've got three groups, so I have to code it. So I'm going to do everything relative to Dominic's own brand. So I'm going to make that a 1 across all possible cases. Then I'm going to have a dummy variable for Minute Maid and a dummy variable for Tropicana. And you can see that if you add these 2 extra dummy variables in, everything would be relative to the baseline of Dominic's brand. I get to see how it affects brands. And again, if I run the regression, I get to figure out my coefficients. So I get my plain vanilla price elasticity, and then I get the interesting effect of the dummies. So I get to see how much Minute Maid brand affects sales, and how much Tropicana affects sales. And again, it's just relative to the reference brand here, which is Dominic's. So that was a quick example just to show you the use of dummy variables and interactions of dummy variables with variables. And you can come up with a matrix summary of what happens to all the parameters under the case where you have interactions and no interactions. Excuse me. Okay, let me do one more example, which I did many years ago, and then I'll update it to 2020. So I'm a keen golfer, and I took a look at a data analytics data set many years ago. There's a famous guy called Dave Peltz, who's written a bunch of books about the short game, and he's trying to figure out what variables affect earnings or affect golfers' abilities. And his books cover a lot of things. I think he used to be a rocket scientist. I think he used to work at NASA. So it's quite mathematical and lots of empirical sports analytics. And again, sports analytics, not just in golf, but seems to have taken off. There's Professor Mark Brody at Columbia University. If you go to his website, he's one of the world's experts at looking at golfing analytics. So Mark's website's interesting to look at. And so, just one simple aside for the golfers. There's no point leaving your putt short. The probability of you getting in the hole if you leave it short is of course 0. So the question is, how hard should you hit the ball? And basically, you should actually aim quite a bit further past the hole than you would have thought. You want to make sure the ball gets to the hole, particularly in birdie putts as well. Okay, so here's a data set I looked at from 20 years ago in 2000, and I'll update the data set and see how things have changed in the last 20 years. So I was very interested to know what are the key variables that would affect money winnings of players on tour. And so a number of events, and there's it'll be a little counterintuitive, but the better players play fewer events, so that'll actually have, in the pure regression, will sort of have a negative coefficient. I want to predict money won, winnings, and then really there's sort of 3 variables. Driving distance, how does driving distance affect things, and over the last 20 years that's changed. And then a key variable that Dave Peltz spends a lot of time talking about is greens and regulation. Basically, the percentage of time that the first tee shot on a par 3 ends up on the green, or the second shot on a par 4, or the third shot on a par 5. One interesting fact about Tiger Woods, I think, is that most of the shots gained that he's had in his golfing career were basically solely on par 5s. And then Dave Peltz is also big on putting. What about average putts? And I think I also have greens and regulation putting. So if you do get to a par 5 and 3, do you actually putt to get a birdie? So now I'm going to do a regression without a transformation. So we can't really look at the coefficients. They don't really make too much sense. But you can sort of see that number of events variable will actually be negative. And of course, the better you are at putting, the more money you're going to make. So any slip up on the putting will cost you dearly. The reason I ran that regression with no transformation is just to see this. Remember, this is back in 2000, just to see how good Tiger Woods was back then. Okay, so here's a regression that has much better looking residuals. And again, these things could be played with a bit further. I could take logs of driving distance, for example, but essentially the key is to take log of money. And again, my number of events has a economically negative value, although it's not statistically significant. And the variables that turn out to be significant are driving distance, maybe not surprisingly, but maybe not as much as you would have thought, or at least back in 2000. And then, of course, the greens and regulation variable and the putting, which again makes a lot more sense. I don't generally talk too much in terms of R squared. Basically, what percentage of the variability of y is explained by those 4x variables. I don't tend to look at R squared much because I'm more interested in looking at the magnitudes and the statistical significance of the coefficients. But one thing I do tend to look at is I look at 1 minus R squared, which sort of shows me how much of the variability is left to explain, just in case I'm missing a key X variable. So, as with all regressions, your conclusions are only as good as the data you put in. So, if you're missing variables or if there's other confounding variables, you need to spend some time thinking about that. But again, it made a lot of sense to me that really the two key variables were greens in regulation, average putting. But we'll see what happens when we update. And of course, now when we look at residuals, Tiger Woods is no longer the extreme outlier, but of course he's still 3 standardized. Remember, the key is to look at standardized residuals, not just pure residuals. We're still back in 2000, we're still 3 standard deviations better than everybody else. I did a little bit of variable selection. I took out a number of events. It doesn't really change the coefficients too much. And again, some of these regression things, you're just empirically pattern matching in the data. So you're just essentially repeating sometimes what should be obvious. So the fewer putts, the better golfer you are, is sort of a duh. But the coefficient is pretty. If you can change your average putts by 1, that's going to be a dramatic change over a course of 4 rounds. And of course, it's not easy to be a good putter. Let's interpret these coefficients. Remember that I'm on a log scale, and so I'm going to transform back. Again, maybe I could have done log of driving distance and log of greens in regulation to see if my residuals look better and if I got a slightly better fit. But let's look at these coefficients. For example, let's look at that 0.16 or 0.16 and a bit. So if I can increase my greens in regulation by 1, so remember that's the number of times you basically have a birdie opportunity. So maybe an incredibly good player would be at a greens regulation of 14 or 15 maybe. If you could go from 14 to 15, then it's going to be a pretty dramatic increase in his earnings, about an extra 18%, or e to the 0.17. It multiply money won by about 18%. And again, Dave Peltz spends quite a bit of time on the short game, and that's one of his key variables. And again, back in 2000, a 10-yard improvement in your drive would have led to a 15% increase. And as I say here, everyone's improved since 2000. So let me update my model and see what happened. So Tiger's going to go from 8 or 9 standard deviations to not quite so much. The exponential model seems to fit well. I didn't show the diagnostics, but they sort of look fine. And I deleted number of events because it had a low T ratio. Again, you can look at overperformers. One of the nice things about outliers, you can look at overperformers relative to a model and underperformers relative to a model. So if you're providing feedback to a golfer, sometimes people go through bad streaks. You can maybe point out that you should have really been, maybe it's not your fault. Maybe you've just had a run of bad luck, and relative to the model, you should have been doing better. Okay, so let's look at 2018, and then let's look at 2020 to see what happens. And rather interestingly, Justin Thomas, Dustin Johnson, Justin Rose, who's done well in the Masters, and then one of the more interesting players to talk about is Bryson DeChambeau. So let's look at him. These are the highest earners. DeChambeau is interesting because the way he trained and changed his physical approach to golf. He's also very scientific, and he started to hit these incredibly long drives to see if that would give him a big advantage. So there's our top players in 2018. Again, relative to the model, you can see who the overperformers are relative to the model, who's been doing well. And you can see who the underperformers are relative to, and names I'm sure most of you don't realize, and they're not doing as well as they should have done. Okay, so fast forward all the way up to this year, to 2020, and again there's the incredible performance of Bryson DeChambeau in this small data set. DeChambeau was hitting an average drive of 344 yards. Matthew Wolff is another big, heavy, long hitter. at 300 and 314. And again, DeChambeau, 5 standard deviations away from the average PGA player. So driving distance was important in 2000, but it's become even more important in 2020. Okay, so I've put go play, enjoy your round of golf, and as I said, sports analytics has become, and golf analytics too has become big business. Look at Mark Brody's website at Columbia if you want to see more things. Okay, so just a summary of regression. What have we learned, and then I'm going to talk about predictive analytics. I'm going to give you some very quick examples that you can look at the links and go over. I won't go over in details, but input data. I like to run the big kitchen sink regression. I like to look at residual plots, outliers, influence. And we've done a number of examples of transformations, and we've done a number of examples of variable selection too. And so, I do variable selection by my T-ratio criterion, and I look at my T-ratios and P-ratios using the summary command. And I'm always attuned to looking at economic and statistical significance. And at the end of the day, I want to make sure that my model is doing well in terms of out-of-sample forecasting. And, as I've said a number of times, the predictive approach to analytics and machine learning in the last 10 years has grown in popularity rather than the causation type approach you want to see if you'll have at the expense of having a more complicated model that you'll have difficulty understanding the causal effects. You'll be only too happy if it gives you good predictions. Okay, so in the last, I think the next 20 slides or so, if you go and click on the links, everything is hyperlinked. Each story is its own vignette, so you could spend a lot of time reading. So I'm just going to very quickly go over these stories. Up to you to go and do some work outside, click on the links, read them. And as I said, hopefully by looking through these stories, you'll get a very good idea of what data science is all about. You get a very good idea of what companies are looking at and what they're doing. So very quickly, the famous Target pregnancy story, a famous story where Target, just based on the purchases of what the daughter was buying, was able to predict she was pregnant long before she told her father. So there was a court case, and the father was embarrassed to realize that Target was right. So regression models predicting pregnancy based on purchases and providing people with coupons to buy things they might have to need. There's a huge literature on understanding consumer behavior. So there's a bunch of MIT experiments. Again, go to the link. Understanding why people buy things and why people do things is big business. I'll leave you to read that one. Understanding habits, how to code people's purchasing behavior is sort of interesting. How did Febreze have such large sales? And then understanding major life-changing events and understanding habits. Can you identify these things from data? So there's a big literature on that. Okay, another famous example from maybe 15 years ago. Walmart has a huge big analytics. One of my ex-students went to work at Walmart Analytics. Began using predictive analytics in 2014, and one of the big findings was when hurricanes are on the way, people like to buy Pop-Tarts. And so how would you stock up knowing that hurricanes are on the way? And there's an incredible logistics network that Amazon, FedEx, Walmart have in place, and a lot of it is based on data analytics, and a lot of it is based on shifting goods before events even happen. So they know ahead of time that people might want to buy things in certain places, and the analytics will tell you to do something before people have even bought. So quite remarkable. I don't know if you've ever thought about the problem of getting deliveries to people inside an hour, but quite a remarkable logistics feat, all run by analytics. The German version of Amazon is called Otto's. The Economist does a nice job of describing how, what type of data sets and what type of regressions that they run. So, they'll look at, in every week, they'll look at 3 billion transactions, 200 variables, and they'll try and build a logistics model to sort of minimize their costs of such things. Again, there's a link. So if you link up here, there's a Bloomberg link to the Stitch Fix CEO, and she talks about how AI is fundamental to Stitch Fix's business. Given characteristics of people, they can predict with certain probabilities what people want to buy and also what recommendations they want to send people. So their business is very data analytic intensive. Uber Paul, again, one of my students went to work at Uber Analytics. Again, Bayes rule is used to figure out the logistics in Uber. Again, a lot of logistics in Uber of predicting what happens. Uber Eats also tracking people, knowing exactly where your food is and exactly how quickly it'll get delivered. We'll see an example of that later. I've mentioned this before, but it's a great website to go to. Kaggle basically describes a predictive culture, and there's a lot of competitions with prizes. Although I do warn you, when you see a $1.5 million prize, also realize that there's 518 teams competing for that, and it's not uncommon for a team to have 20 people in it. So not that easy to win these things. Actually, I've written an academic paper on deep learning and Airbnb's data set. So there's an Airbnb bookings prediction problem, another interesting, very data analytics heavy company that has an incredible data set on cities, countries, locations, people's preferences, and where and what do people want to do. And again, a lot of it is a lot of design of the website to try and help people find things that they really want to look at. And again, if you look at some of these models that they fit, it's a very predictive approach. It's not one of these. You're not going to be able to sit in here and figure out exactly what the causal relationships are. And they have just an incredible amount of data: users, demographics, web session records, and characteristics. And they'll fit things like trees, like XGBoost. They'll fit things like, we'll get to neural networks. They'll fit random forests. And they'll pull estimates from, another big application is they'll pull estimates from lots of different models. Sometimes these multiple models or ensemble methods in terms of prediction tend to do better than just plain vanilla models. Okay, here's another very interesting example. There was a math PhD that wanted to figure out the optimum date for him. So he got zero likes on the OkCupid website until he went and did some natural language processing, downloaded a bunch of data, understood what questions and what answers people wanted. And then I think he went, you can watch the video by clicking on the link, ANOVA video. I think he went straight to the top of the most liked person because he was answering people's questions in ways that people thought were interesting. So that's an interesting, I think he categorized dates into 7 possible groups, and I think he went on, 4 dates a day, and he got to an extreme level of collecting data to understand what was going on. So an interesting example there. One of my colleagues, Vadim Sokolov, has done some dynamic NFL pricing examples. So again, if you click on the link here, you can see a discussion of how people price different seats based on expectations of who's going to win the game, based on other games that are happening that weekend, etc., etc. So another big group of how do you price seats for an NFL game, and a little discussion of here of what happened when it got implemented. Okay, another famous data set that I like to look at is the Bordeaux wine data set, multiple regression. The price of some of these Bordeaux wines have gone from $25 a bottle to like $20,000 a bottle. And again, predicting which one of these wines would become valuable is an interesting regression model. And at the quite incredible, but as this wine gets drunk, 1961 was apparently the best year for Bordeaux wine, and sometimes the prices go to incredible levels. Okay, so I'm going to end. I've got, I think, 10 slides or so on climate change. It's a big topic, so I'll let you click through the slides. There's an interesting NASA article with animation showing you how the temperature change has happened over time, so that's a good link to click on. A stats friend of mine, Peter Gadorp, has spent a lot of his life working on climate change statistics. They're not easy problems, they're time series problems. You don't have that much data. And again, you're forecasting out, 5 years, 10 years, maybe 50 years. And again, you're in a model where you want to try and predict extremes. What's the worst that could happen? So if you read Peter's paper, he's got some warnings there, and quite substantial warnings. 2018 was the fourth warmest year on record. One thing that happens to temperature is it's much more volatile. So you just get more extremes. You get more cold and more warmth. So that's worth reading about. The New York Times has an article. Here's Chicago, and the weather's been quite variable in Chicago in the last few years. Another interesting New York Times link for you to click on. How much hotter is your hometown now than when you were born? So you can see how that temperature has changed in time. One of the data set that I always found interesting was the ice core data set. So people try and dig down in the ice up in Antarctica and Greenland and try and back out what the temperature was. So you can read and understand ice core data sets. And again, there's a nice NOAA link down here for you to look at as well. Okay. And I think everybody knows that CO2 emissions was stable over the last millennium for a long time, and then has been spiking up here. And again, if you read the Peter Gadorp paper and the warnings in there, you'll see more of a discussion of that and why that's important. And again, as I said, I like the ice core data. It's interesting to see what's happened. There's been a number of periods when the Earth has warmed up more than 4 or 5 degrees in the last 50,000 years, if you believe this data, and maybe we're in one of those cycles, and even an on average increase of 2% would just be could be incredibly catastrophic as well. So it's worth looking at. Bill Gates just very recently had a recent book that came out to talk about this as well. Okay, let me finish there. Next lecture is predictive analytics and logistic regression.